I am absolutely delighted to welcome back to the Bavard Bar stage for the third time with an entirely new Bavard on the 7 bridges of Konigsberg. Can we give a huge cheer for Akiva?
Hello everyone, I'm Akiva. I was a maths teacher for 40 years. I taught in secondary modern schools, comprehensives, further education colleges and universities. And I'm particularly interested in the history and philosophy of maths. And this story about the 7 bridges of Konigsberg, it's a true story. It's quite, well, I find it quite interesting. Right, Konigsberg. It means King's Mountain. It was a city in Prussia. Konigsberg was part of Prussia until 1946, after the Second World War, when it was annexed by the Soviet Union and was renamed Kaliningrad. So it's now called Kaliningrad, after Mikhail Kalinin, a leading Soviet politician. It's not actually physically in Russia, it's between Poland and Lithuania. Now in Konigsberg there was a river Pregel, and in the river there were 2 islands in the river, one called Konigsberg and one called Lomsov. And there were 7 bridges joining the 2 banks, the North Bank and the South Bank, and the 2 islands. Now this is a child's drawing that I drew, showing the diagram. So the green, the top green bit is the North Bank, one green bit is the South Bank, the 2 green blobs are the 2 islands, and the red things are the bridges, 7 bridges. So this is how they all connected, 7 bridges. And the names of the bridges were Blacksmith's Bridge, Connecting Bridge, I guess the connecting bridge is the one between the 2 islands. Green Bridge, Merchant's Bridge, Wooden Bridge, High Bridge, and Honey Bridge. Right, there we are. Now, the people of Konigsberg used to go for, we're talking about, 250 years ago, this is. The people of Konigsberg used to go for strolls across these bridges. And they always wondered if they could cross every bridge without crossing the same one twice. No one had ever succeeded, but no one knew if it was possible or impossible. Unfortunately, this lovely activity, the beautiful town, came to nasty end when 2 of the 7 bridges were blown up by Allied forces in the war. I've researched this subsequently, and it seems 2 of the bridges were blown up, 2 were demolished and made into roadways, 1 was reconstructed, and only 2 of the original bridges remain. Now, the mayor of Danzig, which is now called Gdansk in Poland, his name was Karl Leonard Gottlieb. He wrote to the greatest mathematician of his time to ask him to try and solve this problem. Can it be done on a lot of the bridges? And this mathematician, his name is Leonard Euler, not Euler like in Euclid, Euler, it's a German name. And his dates were 15th April 1707, 8th September 1783. And he was born in Basel, Switzerland. Now, Leonard Euler was one of the greatest mathematicians in history, and certainly the greatest in his time. He was certainly the most prolific of all mathematicians. This is a picture of the great man. He created so much new maths and introduced so many symbols and notation that we still use today. For example, he introduced this symbol for pi, the Greekness of pi, which is the ratio of the circumference of a circle to the diameter. What does that mean? Big maths lesson. The blue line is the circumference, the red line is the diameter. Now, if you imagine the red line piece of string, and you take the string and tie it around the circle, it'll go once, twice, 3 times, and a bit at a time. And it's always the same number, however big or small the circle is. You can have the tiniest circle or the most massive circle. The line going across will always fit 3 and a bit times. Now, why do I say 3 and a bit? Well, we can't say what it is exactly. Pi is approximately equal to this, 3.1414. It goes on forever without repeating. It's what we call an irrational number because it can't be expressed as a ratio. You can't have it as a fraction. You can't have it as one whole number over another whole number. That's not a ratio, it's irrational. That's roughly the same as 3 and the 7th. So that's why in schools we're always allowed to use 3 and the 7th to stand for pi. Because it's virtually the same. See, 3 and the 7th is 3.14285, and you can see that they both start with 3.14. So, you know, hundredths of an inch, all intents and purposes, won't make any difference. By the way, talking about pi, there's a book here called The History of Pi. It's a fascinating book. It's going to be made into a film with Meryl Streep and Tom Hanks. No, not really, but it is very interesting. I mean, the author, he's a bit of a fascist, right-wing nutter. He keeps ranting on his fascist music, but if you ignore that, the maths in it is very good. Right. Initially, Euler was reluctant to work on this problem, saying that he didn't think it was a serious or important maths problem, but just a problem in logic. He was right, actually. But he was eventually persuaded to look at it, and as well as solving it, he invented a whole new branch of mathematics in the process called topology. Now, for example, the London Underground map is a perfect example of a topological map. It ignores the physical characteristics of a map, like distances or mountains in the way or whatever, and it just looks like that's how things are connected. So, Euler reduced the problem to a diagram, a network of nodes and arcs. What do we mean by nodes and arcs? Well, the nodes are the bits of land, and the arcs are the bridges. So he made it into a diagram. The top green bit is the north bank, bottom green bit is the south bank, the right hand dot is one island, the other dot is the other island, and the red lines are the bridges. Right? So he made it into a diagram. Now each line is called an arc, or bridge. Each junction is called a node, like the land bits are called nodes. Now, a node, that's a junction where the things join. A node can be an even node or an odd node. What do we mean by that? An even node is a node that has an even number of arcs coming out of it. So it's got either 2 arcs, 4 arcs, 2 bridges, 4 bridges, 6 bridges coming out of it. So that you would call that an even node. An odd node is a node that has an odd number of arcs. So it's got like 1 bridge coming out of it, or 2 bridges, or 1 bridge, or 3 bridges, or 5 bridges, etc. So now look at this diagram. The top green blob is odd because it's got 3 lines coming out of it, which is an odd number. So it's an odd node. The bottom green blob has also got 3 lines coming out of it, which is an odd number, so that's odd. The right-hand blob has got 3 lines coming out of it, so that's odd. The left-hand one has got how many? 1, 2, 3, 4, 5 arcs coming out of it. So that's also odd. So you've got 4 odd nodes. Now, to traverse a network, to go over every arc once and only once, you only have to look at the odd nodes. You don't have to worry about how many even nodes there are, only the odd nodes. Now, this is the tricky bit to get one's head around. Except for the node that you start from and the node that you end on, for every other node, every other junction, every time you go into it, you must come out of it.
Yes.
Because you're not starting from them and you're not ending them. So every time you go into it, you've got to come out of it. So they've got to be even. Right? Therefore, except for the node you start from and the node you end on, all the other nodes must be even. But here we've got 4 odd nodes. So to traverse a network, you can only have either 2 odd nodes or no odd nodes. If you have more than 2 odd nodes, you can't traverse it. In fact, a network, you can't even exist, you can't even draw it, let alone traverse it, if it has an odd number of odd nodes. Now, if a network has no odd nodes, right, if they're all even, then you can start anywhere, but you have to finish where you started. If a network has 2 odd nodes, then to traverse it, to go all of them once only, you have to start on one of the odd nodes, and you have to finish on the other odd node. Now, this is the diagram. So this network has 4 odd nodes, so it can't be traversed. So he solved the problem, but he proved it was impossible. Now, I don't know about you, but when I was younger, I used to doodle lots of different diagrams, see if I could draw it without putting my pen off the paper all in one go. And I spent hours of my life trying to draw this diagram. Right? Now, if you notice, well, let's have a look at all the joins. The tip of each red triangle has got how many lines coming out of it? 2. Yeah, the top red triangle's got 2 lines on the top of it. Each of those 4 red triangles has got 2 arcs coming out of it. Look at the middle, where the green lines cross. That dot in the middle, it's got 4 green lines coming out of it. So it's even, so that's fine. You don't have to worry about the even ones. Now look at the 4 corners of the blue square. Each corner has got 1, 2, 3, 4, 5 arcs coming out of it. Right? So each corner of that blue square has got 5 arcs, which is odd. So the 4 corners of that square are odd nodes. 4 odd nodes. So you can't traverse it. It could have saved hours of my life if I'd known that before discovering oil. But if you knock off one of the triangles, then you can do it. Because, again, the tops of the red triangles have got 2 arcs each, so they're all even. The middle of the cross is even, it's got 4 green lines coming out of it, even. The bottom 2 corners of the square have got 4 lines coming out of them, so they're both even. It's only the top two corners of the square have got 5 arcs coming out of them. So you've got 2 odd nodes. So you can draw that. But you have to start on one of the top corners of the square and you have to finish on the other top corner of the square. So in future, if you're doodling and you want to see if you can do it or not, let's find out if it's possible or not. Anyway, that's it. I hope you found it a little bit interesting.
Akiva Solemani, everybody. Everyone's favourite maths teacher. Wouldn't everybody want to have Akiva as their maths teacher?